I'm gonna set it on the table, and you guys gonna see angular momentum in action.
Whoa!
That is so cool.
Whoa! Oh my god!
So what we have here is that this desk is not moving, but the other one is rotating since I have a motor here. Hello YouTube, my name is Abdullah Kiswani, and today I'm going to give you an introduction to statics. To start, let's give you a definition. Statics is basically the study of how objects behave when they're not accelerating. Meaning if they're standing still or moving at a constant velocity. When standing still, that's called a static equilibrium, and when they're moving at a constant velocity, that's called dynamic equilibrium.
Cool.
So statics can be used to balance objects, or the best example I can give you is when engineers are trying to place supports for buildings. That's when they use statics. Or when they want to design new bridges, like what kind of design should they use, like a pointed arch or a rounded. All these have different properties and different strength, considering the thrust vectors. So the whole concept of statics is we have something, let's say this box right here. We have it standing on the ground, and we have two cables. Now these two cables have to be pulling in the same magnitude of force to keep this object in static equilibrium. So that's the whole concept. So what we can say is that the sum of the forces is going to be equal to 0.
Makes sense.
Same thing for the concept of torque. Some of you are not familiar with torque. It's basically the force that gives the object the tendency to rotate. So as well, sum of the torque is going to be equal to 0. And here are the forces. That's the force vector, as we're all familiar with. F is equal to ma. And torque is basically the position vector with the cross product of the force vector. If we want the magnitude, it's Fr sine theta. So since we have the concepts all done, we can move on to my example of static equilibrium. So what we have here is a wall. Attached to it is a beam, and that's our axis of rotation right here.
Nice.
Attached to the beam is our sign that says physics is fun.
Oh, that's the sign. Oh,
Yeah.
wow, it's coming to life now.
Yeah.
Okay, wow.
Yeah, ignore the corner.
No, that's cool.
And all of these are supported by this cable right here, which have a tension. So to show you our forces, the biggest one is our sign. So this is going to have a downward force, gravitational force.
Quick question.
Yeah.
So the torque force.
Yeah.
That's sine theta because it's the perpendicular force, right? It's a perpendicular component, right?
Yes. And you can also use there's a right-hand rule for the cross product.
Because it's cross product.
Yeah. Good question. So moving back here. So we can say that this sign have a downward force of gravity. So we can say force of gravity of the sign. Our next component is the beam right here. And we just find our center, and we draw an arrow downward representing our force of gravity for the beam. Our third force acting on this system is that cable. That cable have a force going in the left direction, and we're going to call that tension. Now this angle between the cable and the beam is beta. Now I use beta for a reason. We can when we're doing stuff that involve rotation, we cannot use theta for the angle because that's our angular position, and we cannot use alpha because that's our angular acceleration. So that's why I choose beta for the angle.
Running out of Greek letters.
Yeah, Greek letters are
The
limited.
commodity.
Yeah, limited.
So the force of gravity is acting on the center of mass, right?
Yeah.
So it's a symmetric beam. We're taking the center of mass to be in the middle of the beam, right?
Yes.
Symmetrically. Got it.
Yeah, and also we're walking down vacuum boulevard, so there's no there's no wind, there's no air resistance.
Got it.
Yeah. So we had the tension all set up. So let's say, for example, we snap this cable. This whole system is going to collapse in that direction. So we're going to say this is our axis of rotation, represented by A. And every axis of rotation have a horizontal and a vertical component to it of force. So this is our vertical right here, and that's our horizontal. Now they're not equal, but I'm gonna define them in a second. So we identified all of our forces. Now, in every physics problem or static, we're going to have our free body diagram. And the easiest one to do is basically collapse all of these forces into one point, which I'm going to do right here. So this point right here is going to represent our whole system. So to start with, we're going to do our force of gravity of the sign. That's our biggest one. It's pointing downward, as well as the force of gravity, that's a G, for the beam. We also have our horizontal and vertical components of the force, and the tension with angle beta. So these are all of the forces acting on our system. Now there's some people who can take this diagram and move on forward.
Wow.
But there is a second free body diagram, which I believe is a little bit more helpful for people who are starting. So what I'm going to do is represent this beam as a straight line. I'm going to take this line as the beam and draw all of my forces based on that line. So I have in this corner the force of gravity for the sign, force of gravity for the beam or cable at angle beta, the horizontal and vertical components, that's A. And what I can add to it as well that I couldn't do on the point free body diagram is I can add the length of the beam. It's not given, but you're going to see in a second that we actually don't need it, but it's going to help us.
It looks
derive
better
equation.
than the other one. Like, it
Yeah,
looks
for
like
sure.
It represents the,
Yeah,
the
you- mhm.
yeah.
Yeah.
It represents the problem like better.
True.
The other one is like you're putting all the forces on the same axis, which I guess is okay, right? But,
Yeah, it's okay. Like there's some people who can take this and move on.
but it's both are correct.
Both are correct.
Wow.
Yes.
Okay.
Well, especially now, because with the second one, you can take better into account the torque and things like that. To where
True.
with the regular free body diagram, it's harder to see that.
It's harder to see that. Yeah, that one looks like more like what's going on
Right.
in real life in the physics is fun sign vacuum boulevard
Right.
scenario.
Of course. We also I added the L over 2, which is the position of the force of the beam with respect to the axis of rotation. So that's L over 2. So now we have a completed free body diagram. We can move forward. So, wait a sec.
Yeah, I think it's thunder. When you said that, it thundered. Move forward.
So, so let's look at our givens. We are given the mass of the sign, mass of the beam, and the angle. So what we can identify first is the force of gravity for the sign, which is MA, which is going to be 80 kilograms, because that's the mass of the sign, with acceleration, which is G, 9.8 meters per second.
Squared?
Second squared, here you go.
Yeah, I know some stuff. A little bit.
So I already worked this out. 80 times 9.8 is gonna give us 784. And we use
Newtons?
newtons because that's a force. The next one we can let's plug this in actually. 784 newtons. Our next force is the force of gravity for the beam, and that's also MA. I don't want to rewrite that. It's 10.0 kilograms.
What a great formula. MA, like.
It's a life-saving.
It is. I would say physics is F equals MA. Like,
That's it.
it's so much.
Mm-hmm. And we don't need a calculator. That's a 98.0 newtons. We can plug that in right here.
Very nice.
So now we have 2 of the 5 forces already
Mhm.
figured out. I'm gonna erase this to.
Those are both going down. Can you just add them up, or is that like super wrong?
I'm gonna add them up in a second.
You can't. Oh, so
Oh,
it's,
yes.
so because it's going in the same direction, right?
Mhm. Yeah. So what we can do to find the tension is going back to my beginning of the lecture. We said that we have to have sum of the torque equal to 0, right? So we can take this a step further and see all of the forces that are gonna act on the system of the beam and the sign to rotate it. So the first one is the tension. Since we have a force at an angle, that's gonna cause a rotation. So we can say that the torque is force times the distance sine theta. So our force is T. Our distance is L, because it's have to be the distance between the force and the axis of rotation. So TL sine 35, because that's the angle right here, beta. Next we have the force of the sine. It's going downward, so that have to be a negative. The force is 784. The distance is still L, and our angle is 90 because it's going downward. We can do the same thing by applying sine 180, and we can put a positive here. But for the sake of introductory problem, we're just gonna have the negative on the sine 90.
Quick question.
What's up?
So, I just want to drive this point home a little bit more with the sum of the torque being 0.
Yeah.
And that's because it's an equilibrium problem. So all the forces are going to, it's an equilibrium, it's going to balance out.
Yes.
And it's interesting that there's still a torque being applied. There's still some force wanting to turn it, but it's counterbalanced by
Yeah, everything is counterbalanced to have a sum of torque equal to 0.
Got it.
Good question. So our next force is the force of gravity for the beam, and that's going to be 98.0 newtons. Now we have the distance is L over 2 because it's in the center. So L over 2 sine 90.0. And this whole thing equaling 0. Now realize I didn't add the H or the V because those are attached to the axis and they don't cause any rotation. So these three forces are the only one for.
It's because the torque is the perpendicular force times the distance it is away from the axis of rotation, and that we're calling that 0 because we're calling that the stationary point.
Yes. Okay. Good. So we have to solve this equation. The first thing we can do is canceling our sine 90s. Those are 1.
Trig.
Yes. Great. Using
there
our
you
math,
go, Leaf.
using our math skills right
it's
now.
useful.
Yes. What we can do next is also pull out an L from these three and divide it by 0. So that's gonna just go away as well. So we can rewrite it as T sine 35.0 minus 784. These are canceled to 1, and minus 98 over 2. We still have the 2 over here, and
Beautiful.
that's gone. We don't need that anymore. So 98 newtons
Equals 0.
all of that equal to 0. Go ahead.
This is kind of a dumb question. I know a lot of people, like I've noticed, I've seen other physics people like teach. They always include the units in all of the calculations. Is that
Yes,
really
it's a must.
important? Why? Why is that so important? I need to realize.
It's physics, I guess.
It's physics?
It's something about physics.
I guess because you might forget that units at the end. Kyle, do you have any input on that? Or?
I would say, I mean, it depends on the calculation you're doing. Most of the time, we just skip it to the end.
Okay, just depends.
But if you want to write all the units, it helps you keep track and make sure everything's consistent.
Right, make sure you're like doing like
that's
bad
the-
physics.
Yeah, that's what they teach you in physics 1 and 2. Like
Right.
always keep the units. But I believe like when you go on with your physics
Right.
classes,
You should already know what the units are going to be.
yeah.
Yeah, you should be able to look at the computation at any point in time, and be like, okay, those are the units there. The units there are meters per second cubed, whatever that means.
Right, but it is good to help you keep track that everything is consistent. Right?
Cool. All right, cool. All right.
Good. So now we have one variable, and the rest we can just solve. I mean,
Solve for
this
big
is
T.
Still simple algebra. So T is 784. We're gonna move it to the other side, and 98 over 2. That's 49. So adding those together, that will give us 830 something. Hold on. 833 newtons over sine 35. And our T is 1450 newtons. So that's the force of the tension.
That's a lot.
Yeah. And this is still a simple problem.
Yeah.
It can get way harder.
This is like very basic.
This is like what you learned probably on the first day.
No way.
Yeah.
So this is the first day of statics.
Mhm.
Day one.
Day one.
Statics. This is it.
Yeah, probably.
Wow. What's the prereq for this class?
You have to have physics 1 with calc done, and I believe calc 3 done, because after this is a lot of 3D vectors and 3D forces, like
You have to graph 3D
all over the
forces?
oh yeah, all over the place.
On curved spaces and stuff. I'm
Yeah.
assuming, right?
Mhm. So we have our tension, 1450 newtons, and That's good. All right, let's erase that so we have more room. Our next thing is we said that sum of the torque equal to. All right, so power went out and we're back here. So last thing we did was we found the tension on this cable. It was 1450 newtons. So our next step is to say that sum of the forces is equal to 0. So since we have a 2D problem, we're going to have an x and a y component. If it was a 3D problem, we're going to have x, y, and z. So to start, let's do the simplest one, which is x. So we're going to say that sum of the forces, this is dying on me here. We're going to say that sum of the forces in the x direction, that's a good marker, equal to 0. So we look at our free body diagram and we see that H is going H is a force in the positive x direction. So we're gonna have H as 1, and these two are in the y direction, so we don't worry about those. But our tension have an x component,
Right.
and it's negative. So we're gonna see that we're gonna say that negative t, which is the force, and we're gonna have the angle, which is gonna be cosine.
Ah, right. I was gonna say it, but I didn't want to say the wrong thing. But I thought it was that. I did.
Yes.
I did.
Yeah, you're absolutely right.
I feel better. Like
Yeah.
my mind.
It's good you're projecting that.
So moving on, we can just solve for h, plugging in the t. So this is 1450.
Cosine 35.
Yeah, we moved it to the other side,
Yep.
so now it's positive.
Yep.
Cosine 35, and our h is 1,190 newtons.
Very nice.
So we can write that over here.
Day one of statics. So crazy.
So now we have our x direction figured out. We have to do the x direction done. We have to do the y direction,
Y direction.
now. Yeah.
Same thing. Sum of the forces is 0.
Sum
Right?
of the forces in the y direction equal to 0, and we have to see what forces we have. So to start, I like to start from the left and move to the right. So we have V is applied in the positive y direction, so we're gonna have that. Next, H is in the x direction, so we don't have to worry about it. We have force of gravity for the beam. That's in the negative y direction. So we're gonna have negative 98.0 newtons. And also we're gonna have force of gravity for the sine in the negative direction.
Negative
So that's negative
784.
784 newtons.
Yeah.
And we also have the force of the cable, but you have to realize it's in the positive y direction. So we can have a positive t
Sine.
sine 35.
35.
It's like you have a master's in math.
Or cosine perp.
Hey, just use that one.
No, I'm gonna stick with my. So we can plug in t, and we're gonna solve for v.
Solve for V.
Yes.
Right.
So 98 and 784 will give us 882 newtons, and we're gonna have that in the negative because we're gonna move that to the other side. So it's 1450.
The T sine 35 degrees.
degrees, and V is. So the power went out, but the static still continued.
Woo!
So we
now the
stopped
statics is moving again.
at a constant velocity.
Yes.
Hey.
Never give up.
So we stopped here. So let's just, this we can plug into our calculator, and we're gonna get that V equals 49.0 newtons. So now problem is complete. We have all of our forces figured out, and I hope you guys enjoyed this static equilibrium problem. What I have for you next is the dynamic equilibrium. So I'm gonna ask my cameraman to move the camera for me. What I'm gonna do here is I built this thing that's called a gyroscope.
You built that?
I'm gonna set it on the table, and you guys gonna see angular momentum in action. Here we go.
Whoa!
That is so cool.
Whoa! Oh my god!
So what we have here is that this desk is not moving, but the other one is rotating since I have a motor here.
Wow.
And this will give it an angular momentum with an opposite torque, and it will just, ideally it will just stay in place and move at a constant,
Desk is probably dented.
That's freaky. How does it stay balanced like that?
I can actually
I
explain
mean,
it.
because if one of the sides is heavier, like how does it stay balanced?
Here, I'll do it really
It's like
quick.
magic or something. Like
There's no
Let's see
such
how
thing
we'll
as
spin this.
there's no such thing as magic. So what we have here is that
Wow.
this we have this desk right here.
the math sorcerer. No, go ahead. I'm kidding.
Super bad. Okay, so we have this disk moving at an angular velocity in that direction. Angular velocity is the letter. What is the
Omega?
Omega.
Omega.
So and we have it connected over here. So this is our vector, and this disk have a force of gravity going
Right.
downward. So we have this force of gravity. So when we have a rotation like this, we can just curl our fingers in the direction of rotation, and we're going to have our angular momentum in that direction. So
I
it's going to
see.
be this way. That's L vector.
Uh-huh.
And we also have another cross product of the position with the force. So we put our fingers in the direction of the vector, or R, and curl it with the force, and we're going to have a torque in this direction.
Mm-hmm.
So that's torque that we just talked about in the video. So basically, L is what keeps it standing, and the torque is what spins it, and that's how it's just
Cool.
freestanding. I
Beautiful
guess.
stuff.
Yeah.
That thing was awesome.
Yeah.
So good.
So thank you. Make sure you guys like, comment, and subscribe.
Thank you.
We'll see you in the next video.
Thank you. Awesome.
Thanks.
Take care.